Hi, I'm Alex Martyr, a postdoc at CATA, and I'm going to talk about vrfinder, which is a technique for finding outbound addresses in Traceroute. So first, a quick overview of the talk. I'll start by covering what I mean by outbound addresses and how L3 VPNs are a primary cause of outbound addresses in Traceroute, and I'll also show that outbound addresses can negatively affect traceroute analysis using real traceroute output. Next, I'll discuss the vrfinder methodology and go over some of the main challenges for finding outbound addresses. And then I'll end with some results. So first things first, what are outbound addresses in Traceroute? Well, let's say you send a Traceroute probe, the probe expires at some router, and then the router replies with an ICMP time exceeded packet. We generally expect that the reply will use a source address that corresponds to either the inbound interface or some off-path interface. The inbound interface is the interface that received the traceroute probe, and this is the most common reply type in Traceroute. Now, some routers always reply with the inbound address, but others use the address of the interface that transmitted the traceroute reply. When this is different than the inbound address, the reported address is considered off-path, since the probe packet does not traverse that interface. And lots of work seem to assume that the inbound and off-path replies account for all of the responses to traceroute probes. And what we showed in the paper is that there's actually a third type of response that we call the outbound address. Here, the router reports the address of the interface that would have continued forwarding the packet toward the destination. And these responses are fundamentally different from the inbound and off-path responses, which come from the traceroute sources side of the router. They indicate the interface that received the probe or that the router used to reach the source. The outbound address, on the other hand, is on the destination side of the router. Before I show how this can affect traceroute analysis, I first just want to go over the primary source of these outbound addresses, Layer 3 VPNs. So Layer 3 VPNs allow a network to multiplex its network infrastructure, basically creating separate virtual networks in addition to the default forwarding network. It's usually run on top of an MPLS backbone and allows a service provider to enforce various routing policies, such as which networks are allowed to exchange traffic using the service provider's network. Here we have a service provider with an MPLS backbone and 3 other networks interconnected with the service provider. Here I'm showing the default forwarding network, and ASA and ASC are both connected to the default forwarding. When a traceroute traverses the default forwarding network, even when there are L3 VPNs, nothing unusual appears in the traceroute. Here, all routers responded using their inbound addresses. But the L3 VPN is a different story. First, only ASB and ASC can communicate using the L3 VPN. But ASA cannot exchange traffic over the L3 VPN. Second, when a traceroute reaches the exit router of an L3 VPN, we get a weird response. Rather than report the inbound or off-path address, the L3 VPN exit router, SE3, reports the address of the interface that would have continued forwarding the packet toward the destination. And this unexpected behavior has a negative impact on different topology analyses because it violates normal traceroute assumptions. Here, I'll show the impact of AS operator inferences using the border map it tool. So at the top is a traceroute through Internet 2's commercial peering L3 VPN that revealed an interconnection between Internet 2 and Google. The real topology, which I confirmed with Internet 2 routing configurations, is that the interface I2 is an outbound address on the Internet 2 router R2. But border map it inferred that it was an address on a Google-operated router, and it's not hard to see why. If we assume that traceroute responses are inbound or off-path, then the 2 back-to-back Google addresses is a very strong indication that the first address is on a Google router. The outbound address violates that assumption, and in this case leads to the incorrect inference. So now I'll discuss how vrfinder finds outbound addresses and some of the challenges that we encountered and dealt with. So to try to keep the intuition behind our approach simple, here's a network with 3 routers. And just to ensure we're all on the same page, routers interconnect over IP, so the IP addresses of the interconnecting interfaces need to be in the same IP subnet in order to communicate. Typically, when interconnecting 2 routers, network operators use a point-to-point subnet. And in IPv4, that's either a /30 or /31 subnet. So now we have a traceroute where all routers respond with inbound addresses. And importantly, none of the responses came from the same interconnection subnet. And the same thing is true when we get off-path responses. But here, R2 responds with the outbound address. As long as R3 responds with its inbound address, we get the unusual traceroute output of back-to-back hops with IP addresses from the same point-to-point subnet. And we use this as the basic inference method in vrfinder. We look for traceroutes that contain back-to-back addresses from the same point-to-point subnet to indicate the first address is an outbound address. Now, a couple of limitations are immediately apparent. First, we need the router following the outbound address to both respond to traceroute and respond with its inbound address. Otherwise, we won't be able to identify the outbound address. Second, our technique is specifically geared to point-to-point subnets, but some subnets interconnect more than 2 routers. And we can recognize when this happens with IXP public peering addresses, but otherwise we'll miss the outbound address if the addresses are not consecutive. And there's a lot of challenges that we discuss in the paper. One is that while I mentioned that we account for larger subnets used for IXP peering, we also need to differentiate between inefficient peering and outbound addresses. 2, we include heuristics for finding outbound addresses prior to a router that didn't respond to traceroute. And then for these last 2 challenges, I'll provide a little bit of detail, since they are the most prevalent challenges that we faced. The first challenge is forwarding loops that look like outbound addresses, and the second are 2 address subnets that look like 4 address point-to-point subnets. In both cases, we might mistakenly infer outbound addresses. The problem with forwarding loops is that they resemble outbound addresses in traceroute output. Here, the traceroute reaches the router R3, but then doubles back and loops between R2 and R3. The adjacent traceroute hops, in this case the interfaces I7 and I6, both have addresses from the same /30 subnet. But I7 is not a forwarding address. And this case we handle by removing address loops from traceroute paths before inferring outbound addresses. And then here we have a similar situation, but it's actually much harder, because the address loop doesn't complete. Rather than returning the probe packet to R3, the router R2 drops the packet. And this happens a lot with source address validation. In this case, we can't just remove the address loops because there are no address loops in this traceroute. So to catch these forwarding loops without an address loop, we send a follow-up traceroute to the address we think follows the inferred outbound address. In this case, we send the follow-up traceroute to I6. Now, if I7 is a real outbound address, then this follow-up traceroute should still see I7 followed by I6 again. Otherwise, if it's really some sort of forwarding loop, then we expect the traceroute to end without revealing the potential outbound address. And that's what happens here, where the traceroute ends at I6 without exposing I7. And then the last challenge I'll talk about are 2 address subnets that look like a 4 address subnet. Here, 2 responses, I3 and I5, from separate /31 subnets appear back to back in the traceroute. And even though these addresses are actually from /31s, they are potentially usable host addresses in a single /30. And this leads us to incorrectly infer that I3 is an outbound address. To differentiate between /30s and /31s, we send pings to each address in the potential /30. In a /30 subnet, the first and last addresses are unusable addresses, so they can't be assigned to router interfaces. But the two middle addresses are both usable host addresses. And so if we get a response from either of the two unusable addresses to our ping probes, then we rule out I3 as an outbound address. So now I'll discuss how vrfinder finds outbound addresses and some of the challenges that we encountered and dealt with. To evaluate vrfinder, we used IPv4 and IPv6 traceroute collections from CADA's January 2020 ITDK. And running vrfinder on the traceroute collections revealed that 5.8% of the IPv4 traceroute responses seen prior to the last hop of the traceroute were inferred to be outbound addresses. And in IPv6, the outbound addresses accounted for far fewer of the traceroute responses, accounting for only 1.7% of the responses. And then we also validated vrfinder's inferences against ground truth from two large REANNZ networks, Internet 2 and REANNZ. Internet 2 uses its default forwarding network to connect member networks and its L3 VPN to connect some of the member networks to commercial peers. For Internet 2, we had both interface addresses used in the default forwarding network and in the L3 VPN. And vrfinder didn't have any incorrect inferences in Internet 2, and it had a true positive rate of 95.3% in IPv4 and 91.5% in IPv6. So it was able to identify almost all of the outbound addresses in our Internet 2 ground truth. And then REANNZ connects all of its members to L3 VPNs, so we didn't see any default forwarding addresses in the traceroute collections. That meant we couldn't evaluate false outbound address detections in REANNZ, but we still evaluated the true positive rate, which was worse than it was for Internet 2. And the main reason for the lower true positive rate is that many of the routers that followed outbound addresses in Traceroute didn't respond to Traceroute or any of our follow-up probing. So we weren't able to identify those outbound addresses. And then the last thing I'll talk about are modifications to border mapit. So I mentioned earlier that outbound addresses pose problems for border mapit when it infers AS operators for the IP addresses and routers seen in Traceroute. So after inferring outbound addresses in the Traceroute collection, we modified border mapit to account for them when inferring AS operators. Now I don't have time to talk about how we modified border mapit, but that's all in the paper. So first, we looked at the improvement for the Internet 2 and REANNZ L3 VPN addresses. Our modifications increased the accuracy of border mapit's AS operator inferences by 9.5% to 29.1% for the L3 VPN addresses, showing that the inferred outbound addresses significantly improve border mapit's accuracy for L3 VPN addresses. And then second, we evaluated border mapit's accuracy for default forwarding addresses in 5 other validation datasets. And our modifications had nearly no effect on these inferences, showing that our modifications properly discriminated between outbound and normal traceroute responses. So to wrap up, I discussed that outbound addresses appear in Traceroute and that they can complicate Traceroute interpretation and analysis. We created vrfinder to infer outbound addresses in Traceroute using back-to-back addresses from the same subnet. We validated vrfinder against ground truth from Internet 2 and REANNZ with high positive predictive value and true positive rate. And we used vrfinder to improve border mapit's AS operator inferences for outbound addresses. So that's what I have. Thank you for listening.